Maybe you can put like.
The column
Maybe yeah.
you know.
Good. Yeah. Let me get water real quick.
Hello, everybody. New York, received Diego in '96, right? I think Bartek like a little while.
here, same here.
Names like Tiki Barber. He gave this math Caltech and known brown dwarf, which Museum of Natural History. Professor Aganze, department at MIT. Starts as a graduate of the Institute of program. Gotcha.
I'm back at UCSD. I've had some history or 15, 20. Morehouse Bridge Program, and encourage to consider participating. Hopefully, you see some. This is not like an NSA. But the neighbor brown dwarfs and things. And I want to make sure to often in science in general have been happening over the last several hundred years. You have one thread, new techniques that come in, right? Creative ways of, and on the other side, you got measurements, you got data. If you're at Google, data might be a few measurements made by an astronomer over the course of his lifetime. But in all those cases, those are measurements. Those are important measurements. New technologies to even process those observations. Those are the kind of those flows stream together, and that's where you lead to discovery, and that's where you lead to unexpected leaps in scientific understanding. Things that you never expected were going to happen, things you never predicted that you would see. This combination of data and new technologies. Now, just as an example, here's several hundred years. Mostly Galileo, right? So he's using this new technology that he didn't invent, by the way. It was a Dutch guy that invented, and it actually wasn't even the Dutch guy. It was the Dutch guy's assistant that invented it. It's kind of like the grad student that figures out how to do something, and then the advisor says, "Oh, okay, I'll take credit for that." And then Galileo comes along and says, "I'm going to rename this thing that was called a perspiculum into a telescopia," and then not only did he make all these great discoveries, it was also a pretty good business venture inside too. So keep that in mind. But he, instead of just using this for looking around in the distance, looking at ships coming off to the sea, he decided to point this up into the sky, and he made incredible new discoveries that completely changed our picture of the universe. Right? Literally, up to that point, most of the astronomers, philosophers at the time would have said that Earth is the center of the universe. Right? We see the stars going around us. We see the planets going around us. The observations he made, particularly of the phases of Venus, the fact of seeing moons around some of these other planets and those moons going around those planets really kind of put the nail in the coffin on this whole idea that the Earth is the center of the universe. And we've been slowly demoting ourselves ever since then, right? We're no longer the center of the universe. We're not the center of the galaxy. Our galaxy is not particularly special in any way, all right? So we're one of many planets in even our galaxy, so that's been a big shift. Another person who has really opened up our eyes to different kinds of way of seeing is Isaac Newton. Now, most of you know Newton from mechanics, but how many of you know Newton did a lot in optics in his day? Yeah? All right, so he was one of the people who really started experimenting with what is light made out of and what is color. And one of the experiments he and others did at the time was to take sunlight and pass it through this glass prism and discover that these colors that we see are actually all contained in white light. So white light is the sum of the colors and not just something that spontaneously arises. He was able to discern that. He also did strange experiments with his eyeball, so I'll let you research that as well. So he really, and this, we're going to talk about this because this is really the beginnings of spectroscopy. And that's what this talk is about, so taking that light spread apart and looking to see what you can see. Down here, you can't see him in this picture, but this is a picture of Karl Jansky. If you've heard of radio astronomy, you've probably heard of the term Jansky because it's actually one of the units we use to measure the brightness of the star in the radio. That's, of course, named after this person who built one of the first radio telescopes, which is almost looking like a jungle gym of metal. But he was the first to really to investigate radio emission from space, was able to detect several sources out in space, including Jupiter. And we attribute a lot of the radio observations that we know of today to that pioneering work. All right, how many know this guy? Anybody know who he is? So a lot of people know who he is because he was the mentor of Sally Ride, who was the first Walker. Developed a new technology for telescopes. Usually when you think of telescopes like refracting telescope, reflecting telescope, goes your eyepiece or instrument or something like that. Very shallow glance off the metal, and then you can focus those light beams in that way. And that telescope design is the basis for all of the X-ray space telescopes to see for the first time what the universe is. Right? But that was someone who, again, had a new technology. So all these cases, they're examples of seeing the universe in a different way. Picture like this before. Right? This is the whole electromagnetic spectrum here in units of the wavelength in meters. So we're going from long wavelengths down to short wavelengths. Absolutely tiny things. That's what these other parts of the electromagnetic spectrum. That's all we had access to as astronomers, visible astronomers. Today I'm going to be focusing on the infrared here for most. But just to sort of drive this home, I'm just so So this is a picture of the sun, but it's not a picture of the sun you'd ever see with your eyes. You should never look at the sun, by the way. The picture I say that. No, yeah, really. But this is it's a UV. These sort of false color picture like this. But UV is a high energy radiation, and so these particular observations are very sensitive to the outbursts that happen on the sun on a regular basis. And so all these sort of like explosions happening on the sun events produce. And we can detect the UV. Communication satellites. Yeah.
This might be trivial question, but is it true that in over 12 we were almost vaporized mass.
We wouldn't be vaporized. I don't think we've
Or
had
like
anything
just cooks
quite
away
that bad.
to a very toasty crisp. So I was reading around, and the internet is the internet.
The internet is the internet, that's true.
It was not mentioned to be pandemonium.
Large waves of charged particles are away. It's nowhere near enough to like heat up the planet, and actually most of it's deflected away by the magnetic field of our Earth. And what really happened, the big problem is that even though the charged particles get caught by the magnetic field of the Earth, we got satellites in those parts of space, and some of those are exposed out of the magnetic field, and some of them interact with the magnetic field and get toasted that. So it would toast satellites, but we're pretty safe. Yeah, we're pretty safe. And solar storms are solar storms before, the 18th century, no one probably even cared about solar storms because they had no effect on anything. Only after we started developing electronic systems that these solar storms are interacting. So they cause billions of dollars in damage and power outages, but we'll be, we won't get sunburn or anything like that. Fine. All right, but again, a different view of the sun gives us a different view of the physics of the sun, and that's part of the merge of technology and data. All right, here's another example. How many of you seen Jupiter through a telescope? Jupiter? Yeah, get a telescope out here. Here's a wonderful. You can, this is the kind of thing you can see with a pretty big telescope. You can see this with, just like if you go to like a star party or something like that, someone's got a big telescope. You can see Jupiter just like this. You'll never see Jupiter like this, because this is what Jupiter looks like at radio wavelengths. I mentioned those radio telescopes before. That's what Jupiter looks like. And you can see there's a little bit of a planet there, but then there's all this other stuff. It looks like a TIE fighter. Star Wars. Right? This is all the magnetic field of Jupiter. We're outlining the actual magnetic field of Jupiter with this kind of emission. The emission is coming from electrons trapped in the magnetic field of Jupiter. So we get to see a structure that's invisible to our eyes when we look at different planets. And that's also, again, very important in the physics of the planet itself.
This is radio?
This is in the radio, yeah. So 21 centimeters. 21 centimeters is a very famous wavelength. Anybody know why? Was it? Anyone heard of 21 centimeter before? So the hydrogen atom, right? There's a spin-flip transition. You can go spin up, spin down, spin up, spin up. That transition happens at 21 centimeters. Gas out there. So that's right. It's a place to go. All right, one more example. This is another picture of now a star-forming region. This is actually a Carina Nebula, which is light years away. This is a site of star formation. This telescope at visible wavelengths. See these just gorgeous kind of big clumpy clouds, and I should make sure I emphasize that the only way to get this kind of image is we use like very, very normal images won't look this deep. But we can see the clouds very well. The problem is we can't see what's in the clouds. Right? Those clouds are opaque. Infrared wavelengths. That cloud becomes transparent. And now we can start to see, you can see some very red stars in here. These are stars that are actually forming inside that cloud. These are new baby stars that are just forming today. We can directly access the light from the stars by just moving ourselves over to a different wavelength. So these are just kind of examples of how astronomers can use the technology. So this is that are narrowband. Looking is kind of just the emission line radiation from this part of space. And then what they do is they say, okay, this emission line is going to be red, usually hydrogen alpha. This emission line is green, this emission line is blue, and they merge together. So it's not something we would see with our eyes. If you look into space and size, you kind of see kind of a hazy, dusty thing, but it would be nearly this spectacular. They use narrowband filters like this. I have an artist friend that's investigating using narrowband filters to make crazy just photos of around here and stuff like that. Astronomers have been doing it for a while. Have you seen narrowbands? draw it with my arm, but narrowband like this, they just look at that part of the spectrum. So instead of like the whole red or green. Okay, let's get this next one. So today I'm going to talk about another example of how we use different forms of light to discover invisible. They're only visible in the infrared. We call it infrared. You know, why we want to look at stars in the first place. You know, astronomy covers a huge range of topics, right? So you're talking about galaxies and stars and nebulae and planets and stuff like that. But most of astronomy, every time what you're looking at is starlight. Right? It may actually be starlight from a star that you're studying, but often it's starlight that might be, for example, reflected. When we look at Jupiter, we're not looking at Jupiter's thermal emission. We're looking at the light from the sun reflected off of Jupiter. Same thing with the moon. Most of the planets in the solar system we study, they're reflected light. When we look at galaxies, this is a picture of the Milky Way galaxy, right? Any galaxy we look at in space, what we're really looking at is the light from the stars in those galaxies. Even if we treat that as one galaxy, we're looking at the light of 100 billion stars altogether. Other examples, there's a few examples where, like, for example, you're looking at the cosmic microwave background, which is the radiation left over from the Big Bang. That's not stars, right? That's everywhere. But most of the stuff that we look at in space, in some form or another, is starlight or processed starlight. So stars are pretty important for understanding the universe. So it's good to kind of get an idea of how do we astronomers characterize stars. So this is another great, beautiful picture, maybe not as structural, but this is a picture of the Omega Centauri cluster. This is a globular cluster. Globular clusters are really old clusters of stars that probably formed even before our galaxy formed. This one is, in particular, is about 11.5 billion years old. And I'll show you in a moment how we know that. But what do you notice about the stars in this picture? So different colors, all right, lots of different colors. So big, small, or bright, faint? We got more bright or more faint? It's a little, it fools you a little bit, right? Because bright stars are bright. Right? But then look around, look in here. Tons of little stars. And some dark ones. You can't see them. So those two things, the brightness and the color, and the number, are the three main quantities that as astronomers that we care about when we look up at stars and we look up at the galaxy. And so I had this nice video that was produced by the Hubble Space Telescope on how they take a picture like that and turn it into something that shows the patterns of stars. And let's see if I can get this going here.
This is a Hubble Space Telescope image of the crowded core of the globular cluster
it's okay, we don't need
Omega
sound.
Centauri.
Oh, actually, let's try and sound.
The brilliant color.
Or not. It's okay. We don't need the sound. I will narrate. So same globular cluster. Now, what we're doing is we're reordering those stars by color. We're just shifting them over by color. So few blue, few red, lots of white stars. Now we're going to shift them by brightness. Put the bright ones on top and the faint ones on the bottom. When you do that, you get this amazing pattern. Stars versus color. Right? So right now, when we look at the underlying structure of these properties, and the underlying structure turns out to be the mass of stars. So now we go all the way back to our.
And that's the actual.
So here's a cartoon version of that same. Oh yeah, go ahead. I don't know. It's the most brilliant animation I've ever seen. I found. Yeah. So here's another cartoon. So this cartoon is the same plot. Is again it's surface temperature, which is a measure of color. You can see the colors along the bottom. power, physics power, and it's a measure of the brightness of the star. And you can see kind of the pattern you see here is this line that goes across here. We call this the main sequence of stars because most of the stars in the diagram. And again, the thing that dictates where the stars fall on here, right? They can't just be random, right? There's too much structure in there. And what's that? So lifespans is related, but it did something more fundamental than that. Stars live. We call this a Hertzsprung-Russell diagram, named after sort of two astronomers that first thought about this. Russell in particular said we should just call it the color magnitude diagram because that's what it is. It's color magnitude of brightness. People need names on things, all right? So we're going to investigate this main sequence a little bit because it's pretty important. And I said that mass is a fundamental metric, and here's how. So one thing that we know about stars, and we've known since sort of early 20th century, is how they produce all that light. Right? Before the early 20th century, most people would say, well, they start off as really big, bright stars, and they kind of just burn out, and then they become these really faint red stars. So if that was the case, you might think that this line is a line of evolution. Right? A star starts up here, cools off, and becomes something kind of dim and red. Kind of like if you took a charcoal out of a fire. Right? It starts off really hot, cools off, becomes black. So you'll see often when people talk about stars that these are early type stars and these are late type stars. It's left over from the 19th century when we thought that's how stars work. Today, we know that stars are powered by hydrogen fusion, right, in their cores. So you get 4 protons through a series of sequences. You end up making a helium nucleus. And that helium nucleus has a smaller mass than the total masses of those 4 protons. And mass has got to go somewhere. And in these fusion reactions, it gets turned into energy. Millions of electron volts of energy, which sounds like a lot, but it's actually a tiny, tiny amount of energy per reaction. But in fact, there are so many reactions going on in the sun, that's why we get so much luminosity from the sun and other stars. Now, those reactions require a really high temperature and a lot of pressure. And incidentally, that's why we're not today powering all of our devices and our civilization on fusion power. Because the inside of the sun is so hot and so much pressure, we can't actually reproduce those conditions here on Earth. So fusion is going to be something that's very far away off because we simply don't have a convenient little star in our laboratories to contain this reaction. Right? A lot of work is to try to do that. But in the sun, we've got plenty of mass to hold that together, and that's actually the key point. Right? Those reactions are explosive. Right? You know, the nuclear reactions that we see here on Earth often happen in nuclear bombs in the past. Those are explosive. So why doesn't the sun just blow apart? Well, it doesn't blow apart because it's got all of this gravitational mass pushing down on it. And there's a balance, right? Gravitational mass pressure, right? The force pushing in, balances exactly the thermal explosive force from those nuclear reactions pushing out. And a beautiful balance between those two competing forces. It's got to be balanced because we'd have a hard time surviving. So mass helps contain the nuclear reaction. Now that thermal pressure also, the higher the temperature you have, the more these nuclear reactions are generated. And so you drive more power from these reactions. And remember that quantity for power from a star is what we call luminosity. What actually comes off the surface is the luminosity. So the more pressure and heat that you apply to the center of the star, the more energy you're getting out. So there's the connection between mass and luminosity. The last thing, it turns out that luminosity, not of power you're radiating from the surface, is directly related to the temperature of that surface, the 4th power, times the radius of that surface, or the surface area, but the radius in this case of the sphere is the 2nd. This is known as Boltzmann Law. Maybe some of you have heard this one before in your classes. This is a fundamental law for anything that gives off heat, including you and I. We all follow the Boltzmann Law as well. When you get hotter, you start to radiate more energy to the 4th power of temperature. So you know when someone next to you is really hot, right? Because they are radiating heat. Right? That's the Boltzmann Law in action. And that again ties temperature to the mass, ultimately to the mass. All of these observables, how bright the star is, what color it is, what the temperature is, what the size of the star is, all comes down to the mass of the star.
Mass seems to just mass concentrated at 4?
It is actually, yeah. It kind of starts at very, very high density on the inside. The density of the inside of the sun is something like 10 or 15 grams per cubic centimeter, which is more than lead, right? Much more than lead. And as I'll talk about, the objects I study are more of like around 1,000 grams per cubic centimeter, which is the state of matter that you never experience and will never experience here on Earth. All right? But they exist. All right? So yeah, it's much denser in the inside, and then it gets lower density as we go out. All right, so that's just some basic physics about stars, but I think I want to motivate is that the fundamental parameter, the thing we care about most, is the mass. Because that mass controls everything else. Controls the size, the brightness, the lifetime, right? Everything that happens in the star is controlled by that mass. All right, here's that set again, and this is now showing that range of stars. All right, I broke up those blue and red stars. These are now, this is just a cartoon you can get off Wikipedia about what those stars look like as a function of spectral class, and this is just a way of organizing the stars, all right? And I'll talk a little bit more about spectral classes in a little bit later. But the most massive stars, about 40 times as mass as the sun, are also 10 times larger, and something like, let's see, about 40,000 Kelvin, so they're something like 8 times, 9 times hotter than the sun, and they're much, much more luminous than the sun, right? Thousands of times more luminous than the sun. Those are the bright, hot blue stars. Then we've got these little dinky things over here, which are about 10% the mass of the sun, a tenth of the size of the sun, really low temperature, really low luminosity. Those are the ones I study. And I'll explain why in a minute. Yeah, why? Why would you do that? Those are more exciting. I'll explain why these are important. This sequence of letters, by the way, this is like I said, the spectral sequence. Some of you may have seen this before. You might say, last time I took English, that wasn't the alphabet as I know it. It's kind of a long story behind this, but when astronomers first looked at stars and first took their spectra, they organized them in order: A, B, C, D, E, F, G, H, I, L, all the way up to O. Later on, astronomers realized that there actually is some reason why the spectra look that way, some physical reason, and they realized they had these things out of order. And so instead of going back and reclassifying all these stars, we just reshuffled the letters around, which leads to all sorts of fun mnemonics to remember these things. Anyways, all right, so as I mentioned, I study these stars, right? These really bright stars, they go all the way down to something like the sun, something really small. A real simple question that anyone asks, kindergarten would ask, is how small can that star be? If we define a star as something that fuses hydrogen, right? How small can we shrink this thing? Can we have a pocket star, a star that we can hold in our hand? Can I take this quarter and squeeze it down to the size of some tiny, tiny size and make it start fusion reactions, and then I got a little tiny star? What do you think? If I could, I'd be rich. I take a quarter into fusion. It's amazing. It turns out we can't. There's a limit, right? If I tried to shrink that thing down to the point where it would be hot enough to start fusion reactions, I'd have to shrink it down to about 1/millionth the size of a proton. Probably not going to happen. Yeah? Okay? So what's that limit? Well, it turns out the limit's actually a little bit higher, and the limit comes from another force that we haven't talked about. It's more of a physical law than a force, and that's the idea of quantum degeneracy. How many of you have heard of quantum degeneracy before? Okay, so you might get this in a quantum class at some point. The idea is actually pretty simple, right? Two things can't be in the same place at the same time. That's it. You leave every time you try to put your hand through a desk. Quantum degeneracy is betraying you from doing that. All right, that's the sort of. So this is the statement that Wolfgang Pauli said in 1925. But really, this is what it means. You can't put two things in the same place at the same time. The quantum mechanical part of it comes in a little bit later. But instead of saying like two things like my hand and the desk, what we'll talk about is the quantum wave functions. You can't have two overlapping quantum wave functions in the same place, at the same time, the same energy. Right? If you really want to sort of think about it, this is another way to think about it. Right? I don't know if any of you have been to Japan before, but they stuff people in subways, and at some point you can't stuff any more people in the subways anymore. Right? You've reached the subway degeneracy limit. No one's pushing out. They just can't squeeze anymore. In reality, this is more what this looks like. The particles that we're talking about trying to squeeze are actually, it turns out, the electrons inside the sun. Right? And the reason is that I mentioned that this is about quantum wave functions. the size of the quantum wave function scales inversely with the mass. So it's the smallest particles that you have that have the largest wave function. So those are things that overlap the most. So inside the sun, the electrons actually take up more space than the protons do, which seems kind of weird, but that's part of quantum mechanics. So if I have an array of electrons, they fill in the different energy states. So the bottom energy state might be the ground state, very, very quiet. Right? The next energy state's got a little bit of energy, it's jiggling around a little bit. Next one's really kind of going a little bit more, all right? And then we got craziness on the top, right? If I want to put one of these particles and cool it off and put it down somewhere else, I can't because there's no space. All the states, those energy states that I want to put particles are filled. And so those electrons up here, which are jostling around like crazy because they have a lot of energy, and that jostling applies pressure. That pressure never goes away, right? You can't cool it off. It always stays that sort of high pressure. That's when I talk about quantum degeneracy, this quantum force that holds the star together. It's these high energy electrons that you just can't cool off. There's no way to cool them down. And this happens at very, very high densities. As I mentioned, the densities that we'll be talking about are something like 1,000 to 10,000 times the density of water. Things that you don't see in nature. And it's that jiggling that prevents the star from collapsing any further, prevents it from getting hot enough to start fusion reactions, prevents whatever object we're talking about to actually become a star. And this idea was worked out back in the 1960s by two different independent groups. One is Shiv Kumar, was actually at the University of Virginia, a Japanese group. And what they, as theorists, one of the things that theorists like to do is you make something up. All right, you say, hey, I want to see how small a star can be, so I'm going to make up some stars. Make them really small. I'm going to figure out what happens in the physics of these stars as they shrink down and start to collapse, get hotter, and start to fuse hydrogen. Well, this is a plot of that. So this is plotting the core density, right? So it gets higher, more dense as it gets over here. This is the core temperature, so it gets hotter over here. When these the clouds that make these stars collapse, they are getting higher density and higher temperature as they do that. They're releasing gravitational energy into heat. So they kind of follow these trajectories right here. The problem is that at this blue line is when you hit that point where those electrons stop any contraction any further. They provide a firm wall from any more falling in from gravity. And if it gets to that point, or it gets to this magic temperature about 3 million degrees, which is the temperature you need to start hydrogen fusion reactions, then that object will never start hydrogen fusion reactions. It will never get hot enough, never get dense enough to do that. Again, back in the 60s, that's what they predicted. And they predicted that around a mass of about 7% the mass of the sun, you're going to end up with an object that turns out is about the size of Jupiter. And that thing won't fuse hydrogen. It won't behave like a star. It won't have an energy source like a star. And in fact, over time, it will just, oops, I didn't get there. So over time, this thing will actually get colder and colder and colder and fade away, just like a piece of charcoal taken out. Sound exciting? Why would that be exciting? That sounds terrible, right? Like, we're talking about nuclear fusion reactions and explosions, and I'm picking an object that doesn't do anything but fade away. Why would I want to study something like that? Well, it's related to another question, it turns out, a big question that's still here in astronomy. And that question is, what is dark matter? Right? What we do know about this mysterious substance that we call dark matter is that it's got to be around, it's got to be in galaxies, it interacts through gravitational force. And it's something that we can't directly see. Because if we could see it, we'd be able to measure how much of this stuff there was and predict exactly, for example, how stars orbit around a galaxy. So this is a very famous measurement. This is actually from the galaxy M33. What you do is you measure the velocity of the gas going around the galaxy, which you can do through the Doppler shift, just the radial velocity Doppler shift. And you measure that as a function of distance. And you know that gravity still works, right? Newton's laws still apply out in the galaxy. And so you should expect to see that as you get away from the bright stuff, which are all the stars, which are all the matter, that velocity should start to decrease. Just like in our solar system, as you get further away from the sun, the velocities of the planets get slower and slower. Right? That's Kepler's laws. This is kind of the same thing applied out to the galaxy. Instead, what was measured is that these velocities are almost constant as a function of distance away. Much too fast. In fact, so fast people thought that these galaxies should just rip apart. There's no way to keep them going that fast. I'm sad that Saidu's not here because Saidu actually measured this summer. He measured it in our Milky Way galaxy using that telescope that's at UCSD. And same kind of thing, right? This is what you would expect for our Milky Way galaxy of the velocity of the hydrogen gas going around our center of our galaxy. And this is what Saidu measured. And it's not doing that. He was just as wrong as everyone before him. Right? So there's a problem with this, right? There's something missing in our galaxy that we can't see, right? Because this prediction is based on what we see, the stars that we see. There's something else there that we can't see that is still pulling on all that hydrogen gas, keeping it in line, keeping our galaxy from literally tearing itself apart. And that's dark matter. Now, the problem is we know dark matter. There's something called dark matter out there, but we don't know what it is, right? And this is where it matters to a scientist, right? Based on many measurements, the velocity of the gas going around the galaxy, matter also lenses light behind it. You may have heard of things like gravitational lenses before, maybe in the news, right? That's another way that we see dark matter. We see the gravitational effects of dark matter, but we don't actually see it. When we compile all this stuff together, the normal matter, the stuff we're made out of, hydrogen, protons, neutrons, all right, ice cream, right, the Earth, sun, stars, everything that we see, normal matter, is a tiny fraction of everything in our universe, 4%. Right? Lots of Nobel Prizes on normal matter, right? Like, do anything with normal matter, you get a Nobel Prize. Dark matter, which is about 21% of everything, something we don't know anything about. We don't know what it is. We don't know what it's made out of. Right? We don't know how it got there. We don't know how to detect it. That's why the Nobel Prize is up for grabs. You may have also heard of this other kind of even bigger sector here, the dark energy. This is, again, some mysterious pressure in the universe that's causing it not just to expand, but to accelerate its expansion. It was discovered back in the 1990s. In fact, the Nobel Prize was given to the discovery of dark energy about 3 years ago. Again, by the way, nobody knows what it is. This is kind of an embarrassing situation in physics, right? Add it up. 96% of the universe? All the stuff we work on, 4%. Seems kind of trivial. So these are two outstanding questions, not just in astronomy, but in physics today. What is all this dark stuff that's affecting our universe? Yeah.
How do we know that normal matter
good question. So this is kind of an average. If you look at like just a collection of galaxies, let's just take a Milky Way galaxy. If we go back to Saidu's plot, all right? If the galaxy was just made out of normal matter, these are the velocities that we would measure. We have to add basically 8 times more mass into the system in order to get something like this. So it's kind of that ratio of, in this case, it looks like it's 5 to 1, but it's kind of the ratio of how much more mass do you need versus how much light mass, like things that produce light. So that's there are other measurements that are made based on distribution of galaxies in the universe and various fundamental constants, but they all kind of converge on the same number. And it's only a fifth. And only 4% of everything. Crazy.
So organic doesn't reflect light.
So dark energy is the reason that these have these terms is because dark because we don't know what they are. And matter is because it's interacting gravitationally, so we think it's some kind of polar matter. Energy, because what we see manifested is this sort of pressure in the universe that's causing it to expand. So you think about it as like a thermal energy, right? Like you heat up a balloon, the balloon expands. Right? This is something intrinsic to our universe that's causing it not just to expand, but to expand faster. So I'm not going to go into too much detail on that because that's a whole other talk, but if you're interested, take a look at, you can look at the Nobel Prize site. Every time they get a Nobel Prize, they have a nice write-up exactly what's the science behind that Nobel Prize. But it's a big embarrassment, right? We don't know. It'll also be a good opportunity. My job is secure, right? Your job is secure if you go into astronomy because we don't know what to do with this stuff. All right, now, so this is up for grabs. So we should go for this, right? We should see if we can get dark matter. Let's go back to these like kind of boring, small, lame little stars that I've been talking about, right? They're cold, they They lose all their heat. They get really dark, made of matter. Oh. Oh, okay. So in the 1960s and 70s, people got really excited about brown dwarfs because if they're dark and they're made of matter, maybe they are dark matter. Here's another reason. This is I mentioned the three things that we care about when we make measurements: the brightness, the color, and the number. Right? And remember that globular cluster, the small little faint stars were the things that were the most common in that picture. Right? This turns out to be generally true. So this plot is showing, so this is mass on the axis here. It's going from high masses to low masses, or little stars are on the right side. And then this is the number density of stars on a log scale, so you know, kind of 10 million, 100 million, a billion per cubic parsec. I'm not quite sure what the exact number is here. But this is a measurement made back in 1950. Of stars. And notice the trend. Right? It's exactly the same trend that we saw with our eyes in those early images, that there's a lot more small stars than there are really bright, massive stars. Right? Now, one thing astronomers love to do when they see a line is let it keep going. All right? Let's just keep this, let's just go. Right? See how low mass we can get. Right? It turns out, if you push this all the way down to something like the mass of Jupiter, you got all of the dark matter you need. If there are these little stars that are that small in our galaxy, can't see them because they're just really faint, we got it solved. Right? Just a lot of little things. So people got excited because it's Nobel Prize up for scale, right? So here's the problem. If I was giving this talk 20 years ago, I would say I'm kind of depressed because there aren't any brown dwarfs. People looked for 30 years for these things. Tried all sorts of different techniques. Looked around other stars, looked for lensing from these things, all these kind of techniques. Nothing. 30 years. Pretty terrible graduate thesis, if you ask me. However, there's a reason I put 1994 in here, because in fact, it's not that they didn't exist. It's that they weren't visible. Go back around to this idea of different wavelengths, all right? So think about two things. So I live in San Diego. I like to go to the beach. Two of the great, nice, bright things at the beach: sun and a campfire, right? Something you do in the day, something you do in the night. These things are pretty different objects, right? Sun is this big, massive hydrogen-burning sphere of plasma, and fire is something that you just kind of make there at the beach. But there's some observations you can make about these things. So you can measure the temperature of the sun, at least the surface of the sun. You know it's about 6,000 Kelvin. But just in a beach, you know that the sun is a lot brighter than it is hot. I mean, it feels nice and warm, right? But you can lay under it for a while, and you're not going to spontaneously burst into flames. But try to look at it. Don't look at it. Ignore what I just said. Right? It's extremely bright to our eyes. Right? It hurts our eyes. On the other hand, so that means that the visible light, that light we see with our eyes, is much greater than the infrared light, the light that we feel as heat. Right? Now take a campfire. Campfire turns out, it depends what kind of wood you use. What you get, you spray it with lighter fluid, like I like to do, so you can see the bursting flame, right? That's maybe somewhere around 600 Kelvin, about the 10th temperature of the sun. And campfires, you can stare at the campfire all you want. I find myself staring at campfires and forgetting that I'm supposed to do another stuff, right? So they're very hot because you get nice and warm, you don't want to get too close to get burned, but they're not as bright. In the electromagnetic spectrum, the way we translate that is that the infrared light is much more intense than the visible light. So these two glowing objects have two very different properties, and we can really make this measurement even with our eyes. Now, the physical reason behind this is these temperatures control how this object emits light as a function of wavelength. Hopefully some of you have heard of something called Blackbody Radiation. Right? This is the distribution of light that any object gives if it has a temperature. Right now, all of us are emitting light at a pretty low temperature, right? Our body temperatures. Right? Well, I'll show you what that light looks like in a second. Right? The sun, about 6,000 Kelvin, this is what the distribution of light looks like. So this is a function of wavelength. This is a log scale, so we're going from Here's the visible band. Here's some UV range. And here's some infrared range out here. Right? And something for 6,000 Kelvin, you can calculate exactly what the spectrum of that object is, the black body spectrum of that object is. And it looks something like this. And you can see, notice that it peaks somewhere in the yellow band of the electromagnetic spectrum. What color is the sun? Don't look at it. Right? Something like yellow, right? That yellow color has to do with the temperature of the sun. Right? If we go down to a lower mass star, say 3,000 Kelvin, that peaks at a longer wavelength, about 1 micron, which is just outside our visible band, outside the range that we can see with our eyes. But there's a little light that comes in here at the red end of the visible spectrum. Right? What color do you think that star is? So infrared, if we had infrared eyes. For our eyes, it's red, right? I showed you this picture before. Hot stars, big bright blue. Low mass stars, cool stars, very, very red. They're red because of that black body spectrum. Okay? Let's go to the objects I'm studying, or let's go to that campfire, right? Because I study brown dwarfs that are about 600 Kelvin, about the temperature of a campfire. There's the black body spectrum. What color is that thing? Nothing. Right? There's nothing here in the visible at all. We don't see anything at those wavelengths. All of the light is coming out at wavelengths that we can't see with our eyes. So those really cool dark stars that we're looking for, that we hope that are dark matter, are just simply invisible. They're so low temperature that we just can't see them with the wavelengths that we have accessible to our eyes. But fortunately, we have this, remember these two flows, right? Data and technology. We've got technology now that we can observe these things with. We've got technology that's developed over the last 200 or so years. The first person to really see infrared light was this gentleman, Herschel. Herschel is also very famous for studying Saturn. But he did this experiment where he did the same thing that Newton did. He had a prism. He put some sunlight through it, and he saw the spectrum, the rainbow of light that comes through there. And what he noticed is that if he put some thermometers just past the red, right, just past the wavelength that you can see with your eyes, those thermometers registered something. They registered some extra heat. And he conjectured that there were invisible rays of light that were actually coming from the sun that they couldn't see with his eyes. So the first person really conjectured that there was other forms of light that were outside our visible range of radiation. About 100 years later, a group of folks started making actual devices to detect this near-infrared radiation, not just here on Earth, but looking out into space. The first detection of near-infrared radiation from the moon and from the sun and from the stars came in the 1920s. And today we have devices like this. Right? This is something that fits in the palm of your hand. This thing costs about $500,000. I've held one of these things. I've never been so scared in my life. Right? But this is, 200 years of technology development, and we now have something that looks like a camera, a CCD detector, that we can put behind a telescope and look at the sky in the infrared. And that's what we've done for the last about 30 years. Starting with this infrared space telescope in 1983, we now have had several surveys looking at the sky at infrared wavelengths to see what that sky looks like at these wavelengths that we can't see with our eyes. And this is what we see. So this is, I'm going to show you the same picture, same part of the sky. This is reverse image, so the black spots are the stars, the white areas are the background space. Right? It's a little easier to see it this way. I'm going to show you a picture of what the sky looks like at visible wavelengths. And this is a picture of the sky in infrared wavelengths. There's a brown dwarf in here. Which one is it? You want to go back? Okay. You've done this before. All right. There's the visible light. And there's the infrared light. Anybody see it? One more time. Trust me. Trust me. All right. Let me go back and forth real quick.
Oh, right there.
Okay, so sometimes we get lucky, and in space this magical ring appears and tells us exactly where the object is. That's it right there. So here's the infrared. There's the visible. Nothing. Right? Completely invisible star. Right? But as soon as we go to the infrared, bam, easy to see. Right? Whole new class of star that we've never seen before because they haven't had visible light yet.
So if I was scooting around in space, drive into these.
So there's so I'll get to this in a second, but they're still pretty far apart, and there's actually not as many of them as they're not like everywhere you gotta like avoid. They're still pretty far apart. But if you had infrared light, you would see these much easier than visible. Okay. So these first detections were made in the 1990s. Now we have thousands. This is just a website that kind of compiles all these different objects. We actually have classifications, and I showed that letter sequence before for the normal stars. We've now got a few more letters, which are just as much out of order as the last ones were. All right? But the big question, are these dark matter? The answer is no. So we actually see a lot of it. There's probably as many of these brown dwarfs in the universe as there are stars. But remember, they're small stars, low mass stars. We need something that was 5 or 8 times the mass of stars. Now we got something that's like they're back to being boring. But remember, I said that these things are very common. We're finding them all over the place, and some of them are nearest neighbors. So just last year, in fact, one of my colleagues in Penn State discovered the third closest star to the sun. I think there are 2 of them. It's a binary system. Discovered in 2013. We should have found this thing hundreds of years ago. It's only about 6 light years away, and it was only found recently because it's entirely shining all its light in the infrared. In fact, it's so close, if you watch it over the course of many years, you can actually see it move across the sky. It's that nearby. All the stars are moving at some level, but the nearby ones you can actually see crossing the sky. And it's so close that we're actually starting to get some idea of what the surface of this thing looks like. It's actually quite amazing studies. The same colleague this year found a brown dwarf that's the 4th closest system, and turns out to be about 250 Kelvin. Colder than this room. It's cold. It's frozen, right? Just found, just this year. So we're finding lots of really exotic sources that you almost wouldn't consider stars. I mean, something that's colder than ice doesn't sound like a real star, right? But these things exist, and we're now starting to find them. Here's another unusual class of objects: rogue planets. Right? We like to think of planets as things that orbit around stars, but we're starting to see in some of the young star-forming clusters these like little faint stars that, if you consider their mass and their temperature, so you consider their age and their temperature, you infer that their masses are about the same as Jupiter. But they're not orbiting a star. They're just going around by themselves. How many of these things are there out there? We don't know. Right? We're just starting to find the first ones. But what do we call this thing, right? We think of planets as things orbiting stars, but this is something that's like a planet that's just wandering around by itself. Did it get ejected from its star system? Did it just form that way? These are questions we're still trying to answer. All right.
Is it possible to do that?
What's that?
Is it possible for a planet to form?
So I'm gonna bag on theory again, Jeremy. So the good thing about theory is that if you make an observation, you can always come up with a theory to explain it. So I didn't mention this, but up in around 1994, when people hadn't found these brown dwarfs, there were plenty of theories that said impossible to form. No way. There's a physical reason why these things cannot form. First, then we found them. So theories have to be revised, right? So the ideas get changed as we start to find these things, and one of the things that we're trying to look at is how we can change ideas of formation and purpose of the planet. Okay.
I got a test class. I got a test exam in a few minutes.
Okay.
Is it possible looking into stars and the stars became dwarfs and so gravitation pulled up as well?
So it may be that many stars form in double systems, so it may be that the interaction of a planet with 2 stars can kick it out. It may have interacted with another planet in that system and just kind of got kicked out. We know in our solar system there was a period where our planets actually interacted with each other, and that's probably how the Kuiper Belt objects were formed. Things like Pluto and stuff like that probably occurred because Venus and Neptune may have switched places at some point in its history. It may have also led to sort of heavy bombardments of the inner solar system, which is why the moon is so heavy. We have these little clues that maybe planets do interact with each other in these periods. So that's a possibility. Okay. All right, just so I can get forward here a little bit. I'm going to skip a little bit on the Spectral. Okay, I'll just mention this real quickly. So I mentioned these different spectral types. But I want to show your stuff, Christian. All these spectral types are based on the appearance of the spectra of these objects. Again, the spectra is taking light and dispersing it as a function of wavelength, making that rainbow of light that we did back in the 17th century, 18th century. And so these are the spectral types that define the M, L, and T class. You can see they all have different shapes and different structure, and all this structure comes from the various chemicals that are present in the atmosphere. And as these things get colder, you get more and more complex molecules. And complex, I mean things like water, methane. These are a list of some of the molecules that we see in the atmospheres of the object: ammonia, vanadium oxide, which is probably not something you see around. All of this stuff is gas inside the atmospheres of these objects, including water. We also see some kind of unusual stuff, like rock, like hot molten rock floating around in the atmosphere of these in the atmospheres of these objects. Right? That has a lot to do with, if you think about it, like if you know what's the hardest thing to melt here on Earth? It's a rock or a piece of metal. That's why we have these big smelts. Yeah, sand. Yeah. If you go from high temperatures down to cold, what's the first thing that frees out? Sand. So we're starting to see weather on these stars that's based not on water but on sand. Crazy stuff, right? So even though they're not dark matter, wow, there's lots of really cool things here. So in the last couple of years, we've been collecting a large sample of spectra of these objects. We've been using a particular instrument called the spectrograph, which is located very nicely in Hawaii, which is a great place to go and collect data. We've had students that have been making all sorts of discoveries with this data just in this last year. This guy, Mike Lopez, has been studying with me, and he's discovered a very young brown dwarf in this sample. And it's probably something that has like a planetary mass, one of these rogue planet things that no one had found before. You know this guy, all right? He's been studying a really cool system where it's a companion to a known star. We know the properties of the star, but we're finding out that the star that he's studying, the companion, the brown dwarf he's studying, is very unusual. Right? We expect it to be totally normal, a benchmark, something we can just trust. Now it's not. So there's a whole bunch of interesting physics that's coming out of just studying this one interesting benchmark. My graduate student is looking at peculiar spectra and noticing that some of them are peculiar not because they have something weird with their atmosphere, but it's because there's two of them. Right? And she's finding some of these binary systems, and one of the great things about binary systems is that as they orbit around each other, you can measure mass. What was the one important parameter that I mentioned earlier? Mass. So we have a way of getting at that fundamental parameter for these sources. Okay, let me skip through here. So I want to just close by mentioning that Christian and Saidu and several others, Jeremy worked this summer on various projects through the Morehouse UCSD Bridge Program. This is something we started just this past summer. This is a program that's sponsored by the University of California, and it's got some pretty good benefits. You come out for the summer, you get $4,000 stipend for working for the summer, so you get paid for your research. You can stay at UCSD for free. We support your travel out there, and we also support travel to research conferences. So Christian is going to be going to SACNIS in October. So is Jared. And then sort of the key of this is, this is Mike from the University of California. They're really interested in getting you guys to start applying for graduate school in any of the UC system, right? UC Berkeley, UCLA, UCSD, whatever. And so any participants who participate in this program will be getting 2 years of graduate support when they go into a graduate program at the University of California. That means tuition and stipend, right? Your pay and your tuition for 2 years. Right? That's something that the universities don't have to pay for because the president's paying for it. So they're like, yeah, free student. We like that. Okay. So just these are the guys that were there. You can talk to Jeremy, talk to Christian about this, talk as I do, talk about their research. And I think I gotta quit, right?
Did you mention about what some of the things you're ready to do next? Well, I mean, they're on the drawing board, but
Oh yeah. So this is kind of phase one of this project. Is we want to get the opportunity for you guys to travel and do research abroad. And I know you've got lots of opportunities to do research at different institutions. So this is going to be one of your many choices. One of the things that we're looking at now is also to help facilitate the transition to graduate school, because that's a big transition for anybody. Is we're starting to develop an idea about not just doing research over the summer, But let's say that you're on the 4.5-year plan, right, or 5.5-year plan, and you're done with all your classes in the fall, and you're thinking about kind of the easy classes to take in the spring. Why don't you come out to UCSD? Take a few classes, do research for about, let's say, 7-8 months. You're going to be way ahead of everyone else. So we're looking at doing that. And in fact, there's already an existing program called the UCSD-Morehouse Spellman Exchange. How many of you know about that? Yeah, so Christian's going on this fall. So we're going to see if we can work with them and also work with maybe another funding source so that you guys can do a transition from Morehouse to a graduate program and get a real big jump start on your research, preparing for graduate studies, and sort of close the loop on getting yourselves into graduate school. For me, and I think also for Dr. Rockford, this is our main interest is that you guys have an opportunity to pursue advanced degrees, because that's where you're going to get the best job prospects. That's where you're going to get the best opportunities. We want to make sure that that's a process that is. Okay.
Got time for about one, maybe two questions.
Yeah.
Exam, they need to get in for the first exam.
We're going to have pizza out there as well, right?
And we have pizza. Yeah, we're gonna wait till they get in here.
Yeah.
Then we're gonna take the pizza out so we can eat out there. Pizza's
I
like,
walk around to pizza no place.
oh, I'm a walker. So, are there any questions or any? Go ahead.
So when you find the cool stars, when it's the aim, because you think that there's not enough of them for them to be dark matter.
Yeah, so they're not dark matter. So why we keep looking at these things? Why are we still doing this? All those things I mentioned, these peculiarities, really cold temperatures, these clouds of dirt, weather dirt, these are all things that we've never seen before. We don't have any physical models. And so, at some level, we're learning. Let's just take the weather things. That's one thing that I'm really interested in. We don't know any planet in the solar system that has dirt weather. But think about how many people work in meteorology just here on Earth, climatology. Right? Looking at different systems is one way of gaining some insight in the system that we care about the most, which is really the Earth. But if we have these other systems that are based on different chemistry or different atmospheric conditions, we get some insight into the general properties. So that's one of at least my particular interest is we find where these objects that have this kind of bizarre weather. We might learn something about weather here on Earth by studying weather here on this crazy star over here. There's lots of reasons.
That's like I was thinking about.
All right, thank you very much.